Alright, we'll got into the group problems. There's another setup here, 4 kilogram slender rod, and you have your horizontal spring, yes, your pin is right here at A and the spring right here at B, and they are in balance, yeah. Of course, you're applying another force right here, 10 Newton, to initiate the motion, and we'll have to find the angular acceleration of that. And the other one is the same thing, the acceleration of the rod's mass center at the instant, 100 Newton force is applied. You have only 3 types of acceleration going on: your normal, tangential, and then your angular, Here we have a setup, and that's in balance, and that's starting in this motion right there. So we're going to use the same R equation, your moment equation, and here is your MMI at G and your acceleration, your angular acceleration here. This one again, I'll measure from your G R distance away, yes, and then of course we're going to put that into there because this mass is that distance away from that axis. So right now, again, you don't have to worry about how to calculate. If you kind of know that, oh, we're dealing with the moment of inertia, mass moment of inertia, angular acceleration, you're okay, for this class. Since we're dealing with the moment, we have distances, that's what you're seeing for each point of it. So 1.53, see, so 2 of that is 3, 1 of that is 1.5, and then of course you have another, this 100 Newton force going down. This is another component of that. It's going to be 1.5 meter away from the point, okay, B, which is the spring is going to be right there. So anyway, so we plug it in and we calculate it, and we'll be getting that, yes. And here we will substitute once you get your acceleration back to the acceleration, yes. That's a 2 component of that. So here you plug this in here, and we have R distance. So therefore you got the 12.5, times your distance R is going to give you this. Your acceleration at N axis is going to be calculated right here with your W, yes, which is given to you actually, I believe. So given to you in your problem, because it is say it's horizontal. So therefore this component is completely 0, no acceleration in that component. So we have only the t-axis component for the acceleration, and you get it from your angular acceleration. All right, then the next one is we have another setup, and we're going to cut this, road, right? And you have this sphere is supported with this rod, and it's kind of like a pendulum, and we're gonna cut that cord, AB, and so that's where your force is going to come in. External force is going to unbalance the system, and here you have your distances away from these points right there. Your pin right here, pin means like where the rod is attached, to the support, and here is your sphere in this pendulum, so it's going to swing this way. So you gotta draw your free body diagram and kinetic diagram, and we're going to take the rod and the sphere as one unit in the pendulum, that's just a system. So we draw the same thing and put our mass right there, and mass with your acceleration due to gravity is going to give you your weight, 30 pound, 10 pound rod, already provided to you in the example question. And here is your pin. We're going to break it down into x, y. See, we always break that down, and then find the force first, and then for each of your axis n and t, we get the sum of the force, So once you get that, we're going to put it back to our same equation again and again, the same thing, plug it into it, and you will get the angular acceleration. And use the angular acceleration. Use that angular acceleration to find the reaction at that point. OY is this, and then OX, meaning like what kind of the total resultant force is going to be at that point, okay? So here we're giving in terms of weight. because of the acceleration, angular acceleration happened here because we cut the cord. Yeah, so it swing, and when the body pendulum begins to move, you want to get the acceleration. Use that acceleration. Yeah, times the mass is going to give you. Yeah, the weight at that. So which is this guy. All right. This one just a little review, yeah, quiz for you. I'll do this for you again. A drum, yeah, here, mass given to you, and we're seeing it again and again. I'm not just telling you. So when you listen to me, you kind of get it, yeah, a big picture of it. That's why I'm trying to tell you again and again, again, and again, the same thing for 3 hours, you know, of the lecture. So you get it. Oh, I'm dealing with a mass, always a mass. There is a force, external force, that unbalance the balance, you know, situation or positions of a system. System always have parts all together. Yeah, the system got to be supported because they have to stay together. So you always have support and something, yeah, that can be able to move. So that's the same problem again and again. Yeah, and you already know we're breaking things. We break the force down, we break the acceleration down, and we break, yeah, everything that we can be able to break into where coordinate system. But there are 2 different types of coordinate system you're using: your xy and your nt. Nt usually deal with the rotation, xy deals with the translation. That big picture gotta be in your head by now, yeah, and me talking to you again and again, again and again, again and again on that. So here we have a drum mass, again mass, and there's some motion going on. Number 1A, by a constant 40 Newton force, and my external force is 40. Yeah, B, by a block of weight of 40, another, yeah, weight is going to be like 40 newtons going to go in there. So if acceleration at A and acceleration at B represent the angular acceleration of that drum in each case, you have to select the true statement. Okay, so is the acceleration A greater than acceleration B, or acceleration A less than acceleration B, or they equal to each other? It cannot be equal to each other. Okay, why? Because you have a constant 40, yeah, and you are in the motion happening in 2 ways. So since the motion is happening in 2 ways, it cannot be the same. Yeah, it cannot be the same acceleration. Why? Because you have no idea what this external force is, even if the amount is the same, magnitude is the same. But one is a weight and the other one is you have no idea what that is. Yeah? So that doesn't mean that it's going to have the same acceleration at point A and B. Not point, I mean like acceleration A and B for 2 different, yeah, the 2 different scenario, I mean. So when you think about it, when you look at it, they're all the same. The only thing that is not the same is you have no idea what this is, and you have idea what that is, which is a block, yeah, weight of the block. Even though we have the same force, yeah, so this thing got to be the same, yeah, got to be the same setup with the unknown force. So therefore, we have no idea. But it said they represent the angular acceleration of the drum in each case. So when you carefully read it, the very first reaction you get is you're going to choose C, and you will be wrong. Yeah, it's because of this. This is constant 40, and this one is it's just a weight. It can be instant. Yeah, just bang, and you got something. So the acceleration, yeah, for this situation got to be greater than that because you have no idea, yeah, how this block is going to react to the system. This one you know because we're giving a constant 40 Newton force to it. So you will always have this acceleration greater than that over time. Again, don't forget the time. Yeah, I say it again and again. If you just think about the magnitude, you're gonna feel like this is greater because you can see anything here. You have no idea what the applied force is about. Yeah, so therefore, this situation, the acceleration generated by this situation is great always. We're greater than that because you have a constant applied force. Okay, this one you have no idea how the force is being applied. In case B, yeah, we have to know the tension of that cable. So the tension, it's this weight is 40, Yes, so the tension got to be less than 40, otherwise it's not going to rotate. Okay, and it's set into motion. It's set it so here, yeah, as it's set into motion in two ways, so it's already in motion. So therefore, if they are equal, it won't be any motion. If that's greater, it won't go down. It gotta be less. The tension gotta be less than the weight, so it will move. Okay, so those kind of things, just pay attention. Or that's just for the next section. Yeah, so let's get into there. So after you read that section 7.3, I think. So you're gonna get this. We're in 7.4, I guess. So the disc roll, after reading, so your disc is gonna roll on a rough surface without slipping. Okay, no slipping, just rolling in balance. So the acceleration of the center of gravity G is going to be, of course, it's going to be equal to your angular acceleration times your distance, and it's going to be less than your friction. Otherwise, it won't go. Yeah, it won't be like rolling. So in order for the disc to roll, it's got to be less than this because it's not slipping right there, and should be equal to your acceleration times r, which is your center of gravity, acceleration of the center of gravity. Your friction force is going to be this, because of the this is wrong right away because you have a friction force. Your acceleration is going to be like this. Your acceleration times r, because we're dealing with the center of gravity G at point G. Yeah, so they all have it anyway. Is it going to be like equal to AR, or this without slipping? So it's got to be less than, and then it's got to be equal to angular acceleration times r. Otherwise, it won't roll. Yeah. Then we have a second one. If a rigid body experiences general plane motion, the sum of the moments of external forces acting on the body about any point P is going to be equal to this guy, because it's asking you moment. Moment of external forces is always this. Your MMI at P times angular acceleration. We've been telling this again and again. Then comes your application. Your application is your SUNY compactor is right here. Accelerate forward, keep going in that direction in motion. The front roller, this guy, is going to experience a general plane motion. That means you are dealing with the rotation and translation at the same time. And how are you going to find the loads experienced by the roller shaft right here, or its bearings? And the force shown on the roller shafts in free diagram right here, cause the acceleration shown in that kinetic diagram. This is your motion diagram. That's just a free diagram. So it's showing you the balance force right there, and you have your weight right here, and your G point right there. Okay, and then your brake, which is your X and Y axis, we break it, and then your normal force, supporting that. I've been telling you again and again. And then we have our external force, in motion, moving in that direction. Since you move, you have acceleration. Mass is this guy anyway, and this is your point, and that point is away, that distance away from here, and that's always your external force, which is your MMI times your angular acceleration. The entire chapter again and again, telling the same thing again and again. So you gotta get this big picture, by the way. The next application, your long roller, we're gonna push it at an angle, and there is your external force 200, and the handle is held at 45 degree. That's where your cosine and sine breaking come when we break the force into components. So how we determine is translation, acceleration, angular, acceleration. We can be able to calculate it, and that's what we're going to study how to do it. So does this total acceleration depend on coefficients of static and kinetic friction? Of course, definitely kinetic. Okay, application. So we have a impact. So since you collide, then you're going to in this direction towards the windshield right there in your car, of course. Vehicle mean in your car, yeah. And then also experience another acceleration due to its rotation about the point A right here, yeah. Because rotation means you're moving bang that way, yeah. That's why sometimes you have an airbag right here to support your face, yeah, so you won't get hit. All right, so we gotta think about why you're moving like that when you just like collide something or abruptly stop it. So how can engineer use this information to determine the forces here exerted by the seat belt, okay, on a passenger, because the seat belt gotta hold you back in order to compensate that force, yeah, from your motion. So these are the things that you calculate when you build the car, yeah. So everything has been here. First we got you've got to do the same thing, your free body diagram, and then compensate all the forces so you won't go and hit the windshield, yeah. So that's how you calculate everything to prevent, yeah, to prevent accidental damages to your body. Okay, that's how we design the seatbelt. The point is the seatbelt gotta have a more force than your impactor force. All right, general plane, so rotation and rotation and translation all together, yeah. Your review again, general plane motion, yeah, constitute both translation and rotation. We're gonna bring our xy again. We're gonna bring our moment, yeah. So this is your motion equation, which is your mass moment of inertia, and then your angular, yeah, acceleration. You should get this by now, at least. Break it down into xy component or nt. Rotation nt, xy your translation. Your force is always na, yeah. And these little alphabets are just showing you where the points are. Oh my gosh. All right, then we get into another one here. Yes, so here we're just getting into determining the point, yeah. So the point, we have two different points going on. One is a G and the other one is a point, all right, in your body, yeah. We see this again and again, the same thing. When you break the forces down, it looks like this, yeah. So you have your Y and then you have your X. We are breaking this, yeah, resultant force down into its subcomponent, yeah. This is vertical and that is horizontal, and your reference point is G, yeah, mass center. Okay, so anyway, we do the same thing again to get, yeah. So one about point G, about point P, yeah, two different scenario we always study. So anyways, it got into this, and here is rolling motion. You have your wheel, yeah, cylinders, your disc can roll like that, of course. We have so many machine based on this, yeah, setup or system, and the body is going to roll. And slipping is very important because we're playing with the friction, yeah. So without slipping, it's going to roll. So you have some control over that system. So what you got to do is first first you gotta come up with your equations of motions. Same thing, we're gonna list out, and yeah, break the forces, your x and y, yeah. Write down the forces formula, and then we are going to bring our angular acceleration with our mass moment of inertia, yeah. So right about before it moves, and we put that all the equations of motion, and then look at what is unknown to us. We don't know the force, we don't know the end point, which is your normal force, angular acceleration, okay, and then acceleration at G. So those are the things that you have to find, yeah, and we always find anyway. So here we have to make an assumption to provide another equation, then we can solve for the unknown. So that's the procedure how to deal with the problem. Right now you wouldn't know, don't worry about it, okay. We will do the easy problem for you, but you got the general picture, and that's all I care about. Your normal force, your applied force, your weight, and then this is where the distance between your G and then the point P, okay. This is a distance, R is your force direction and the point G, okay. So if you know, like, oh yeah, I'm breaking down forces, I have like a point G, a point P somewhere in the body, and I'm playing with all that distances to calculate angular acceleration and also to calculate, okay, whether the applied force is bigger or smaller or equal to the frictional force. Am I slipping or not slipping depends on that balance of this diagram. So if you know about that, it's okay. Yeah. So first assumption, no slipping. So your AG, okay, A mean acceleration at G, which is defined by your distance and your angular acceleration, okay. You can write it with our fourth equation, which is that one. And where are we? Okay, and then of course this is your friction is always mu and then s and then times your normal force right there, because normal force is always acting this way, so friction's constant times the normal force is the resistant force for that applied force. So that's what we're doing here. So if you have slipping, then we're going to apply this, okay? At that time, your AG is not equal to your angular acceleration time that distance. Yeah, that's the only two different. You're slipping, your AG is there, okay? No slipping, AG is there because you are using that, force. Slipping is not there anymore. It's not equal. There's something else that is contributing that force to slip. Okay, the procedure analysis not necessary. Just listen. We usually break it down into XY inertial coordinate system. And then we're gonna draw a free body and a kinetic for motion diagram about to move or start moving. This is imbalance. Free body diagram. And then we're gonna throw in what we know and then find what we don't know. Usually is acceleration at a point G or point P. Okay, you'll always have an external force, and then you always have to find if these forces are in balance, and if they disturb the balance, so what is the amount of your external force. From that external force, you can always get mass or acceleration. When you get the acceleration, we can break that acceleration down into different components. Okay, so that's how the problems are most of the time. Okay, then we get into procedure analysis for dealing with the unknowns. It's kind of like step by step. So you get one step and then plug that value into another equation and get another step like that. So that's what we do when we have to deal with the unknown. So first you solve one value, use that value to solve the next value like that. And then of course, slip and no slip, all the time. I've already told you in the previous 2 slides on how to differentiate slipping or not slipping, playing with your friction, frictional constant or your normal force, and so on. So okay. All right, the very first example will go into a spool right here, and you have a mass of 200 kilogram. It's pretty heavy, and then your radius of gyration, your K, it's going to be 0.3 meter. And then K is a distance, so therefore it's in meter, and then the coefficient of the kinetic friction between the spool and the ground is going to be that, that's the frictional constant right there, your resistant force. So we have to find the angular acceleration of the spool and the tension of the cable. So first we have to focus on something that can move, which is your spool anyway, and then we're going to start drawing your free body diagram and kinetic, which is your motion diagram. I call it motion diagram. This one balance diagram. Your normal, and then you're gonna have your tension going that way, and your rotation is gonna be that way, and then your G, and has a force, and that's going down, and that's your mass times 450, okay, Newton is your moment right there. So moment is always your force taking a distance because the body is in motion, and here is your motion diagram. So we show our angular acceleration and the mass moment of inertia in there, playing with your external force, mass time acceleration due to point G. Okay, that's your mass center G. That is repeated, yes, again and again. So by this time, I'm telling you for 3 hours, I think you should get it. And then we use the same motion, yes, of y direction, break it down, y and x, yes, and then go in, put our M and A, yes, and then you will get your point right there because they are equal to each other. Equal meaning like they're balanced to each other. So if you have external force, we always can be able to find the normal force that is pushing against that external force in balance. Yeah, so when N is going down, the external force overcome and you got the motion. Yeah, that's what the equations are telling you about. And then of course we're using the same equation, the moment equation, and then here is your fourth equation in x direction. The same thing, plug it in. Yeah, and once you get NA, you can get NB. Once you get NB, you can get NA. And from there, you get the angular acceleration. From there, you can be able to get your T, which is your force. Yeah. All right. Concept quiz is going to be like, oh, here we have a spool 80 kilogram. Your radius of direction is going to be 0.3, rotating anyway. So it's on rough surface and a cable on rough, so therefore there's friction, and a cable exerts about 30 pulling cable man just like a rope. So 38 Newton is going to be pull this load to the right of that diagram. The frictional force you have to determine, that's going to be right here at this, because friction is always subjected to your normal force. So your N, to the what direction am I going, you have to find out. Yes, and the AG, so it should be directed, that's your acceleration at G, should be directed to where. So the forces pulling this direction, of course everything is going to go to that direction. So therefore the friction force at A acts to the right and also should be directed to the right. So C is right. Okay, so C is right. Why? Is because you overcome the friction because of this force, because it's set so here. All right, the second situation, it's the same for the situation above. Is the second problem. So the moment equation about G is right here. So what you have to find is, this is just a calculation, so I might not going to ask you. It's just like you've got to apply moment, so therefore you're dealing with the distances. So you're given the force right there, so the distances from here to here is set as 0.75, so we have to put that in. So this is all gone. So you're left with A and C, because the first thing you look for is the moment 0.75 with your force going in FE direction is right here. Even you don't know the direction, you can pinpoint the value 0.75. You don't have that, so it's out. Only this. Of course, the second one, we're dealing with the moment, so you have your force time. Your force is 30, another force 30, and then time, your this little, see the force come off from this, so your distance is 0.2 away from G, so you look for that. It is there, so we can get rid of it and then keep going. So 80. So 80 is your this spool weight. So you still need that times weight times your radius. Your radius is going to be it's kg is 0.3, so we're going to put the square and the angular acceleration. Okay, so they both have it, so we can't get rid of it. And then the last one has the 80 and then times AG. Okay, so which is the acceleration at the G point is right in there. But right now we're just talking about the moment equation, so you don't need the moment at G, because we're sufficient with everything, because moment at about G is you got measuring the distances from the G, so you don't have to include the moment at G. See how that's how you so even if you don't calculate, you still can be able to read it because you understand what's going on. So moment equation about, so this is your key point, about G doesn't include at G, so you get rid of this. So your answer is A. Okay, so, don't follow me, I'm too fast. Too fast, because I've been looking at it all the time. So I know what's going on, but for you probably you have to start reading the book, like I did when I was a student. You have to read. Reading is essential. Without reading you won't learn. You can't just listen to somebody. 3-hour lectures is nothing. but you don't learn anything out of it unless you listen to it again and again. If you listen about 3 times, you got it without reading it. But if you don't listen and you don't read, you probably get nothing. Okay. So group problem, 500 kilogram. Again, you've got something on the truck right here. So that's your concrete culvert is about 0.5 meter. Object is right on your truck bed, and we don't want, so no slip again, on the truck bed. And but you can roll it. It can roll, go roll on the bed like that, and you can neglect that thickness. So they want you to calculate the same thing, angular acceleration, when your truck has an acceleration of 3 meters per second. So we do the same thing, bring our diagram right there. The moment of inertia, is going to be your m and the r squared. So your distance and the times your mass, all right, is going to give you your moment of inertia. And at g, okay, so there's a little point right there. So of course we put our g at the center, and then your normal force, your force, and then this is your motion diagram. You have like a 500 times your acceleration due to gravity, and then your m, okay? Then we do the same thing. Bring our moment equation, the moment equation, plug it in, because they are the same, because the moment equation of the motion about point A, which is this one, is equal to that. So we're going to plug it into that equation with our values, okay? So which we get from here. And don't worry about calculating, okay? You only worry about the concepts, meaning like I might ask you to draw the diagram, Okay, so anyway, we'll come back into here. We're going to throw in all of our acceleration. We're going to break the acceleration into 2 different components, and then we're going to put that back in to calculate the angular acceleration and the acceleration at g. Okay, all right, that's it for this chapter. It's a very, very heavy chapter. All the chapters are heavy, but we still have to cover everything, so bear with me. Just listen, okay? Won't be asking you so many things. No calculations in your exam other than the selected problem. And if I did ask you the calculus part, I will give you that value, so you don't have to calculate, okay? All right, so attention quiz. It's kind of like a review quiz here. So you have this system, set it up. There's a beam right there, and there's a cable holding that beam right there. So 100 kilogram beam is the weight of that. And the moment equation about point A, which is this guy, support is A. So you gotta write the moment equation. Since you're dealing with the moment equation, you already knew that you will be dealing with the acceleration, angular acceleration. So D is automatically out because you have bang, bang, bang. You have only one type of moment equation, so you don't have 3 times, so therefore D is out right away. And then, of course, you will have to deal with this, and since we're dealing with the beam cable, that will come from a 1/12. So this comes from your textbook, to the way all the way to the back of it. Since we're not asking you, so just listen. So that value for the beam, is beam cable is 1/12, yes. And then you're gonna multiply that with the mass, which is 100, and then you're gonna multiply that with your which is the distance square, which is, so everything is the same, A between A and C, it is the same, so therefore we can get rid of it. So the only thing that is different is that. So it's asking you the moment equation about the point A, yes. So therefore, you will have to find, okay, your force time acceleration, which is your external force, which is right here, okay? So that's your g, and then x direction, which is this guy, which is that guy going into that direction, got to be in there. So you will put that into here, Of course, we're dealing with the center g, so we have 4 meter here, so that's going to be 2 meter right there, So the weight is 100 time acceleration, yes, and then that acceleration got to be at center g, because we're dealing with the weight, times, since the point is at the center, you have only 2, Yeah, so this is your moment equation about the point A. Okay, that is not there because you're missing the weight, yeah, the weight of it, the weight at the G center point in answer A. Yeah, so therefore we eliminate A. You might not get this, but don't worry about that. Yeah, just review the moment equation, and you know that you will have to plug in all of that, and this one comes from the back of the equation, depends on your system here. Yeah. And then you have to select the equation that best represent the no slip. Again, no slip is usually dealing with the friction. So when you take a look at it, this is gone automatically just by looking at the slip. So we have 2 right there. Okay, since we're dealing with the no slip, yeah, you'll have to deal with the radius of gyration. The radius of gyration is in K, it's not in S. Yeah, so therefore this one. Because if that is a slip, you're gonna choose this. Yeah. All right. That's it for this chapter. It's a very heavy chapter, so you have about like a 2.5 hours of lecture, repeating the same thing again and again. The angular acceleration, yeah, the moment, mass moment of inertia, moment, yeah, equation. So these things are the main point, and I definitely want you to go over and over again to get the concept. Yeah. So please deal with the concept of it, and we will go lighter equations and the lighter calculations, but you do have to understand the meaning of them. That's why I've been telling you again. Don't worry about the analysis. Don't worry about how to get the values of it. Yeah, in this chapter. Yeah. Okay. That's it for today.